And what is omega in fact? As it is constant, can we write omega as theta by t? Angular velocity equal to angular displacement by time taken. After some time, the particle will be available here. The particle will be available here. So in that interval of time, it will cover an angular displacement theta. So at t equals 0, it is here. After certain time t, the particle will be available at this point. Okay, look at now. So it will, what is the capital T? Time taken to complete one revolution. It is like this. Time taken to complete one revolution. Okay, let me go for its projection along y-axis. When particle 1 is here, what is its projection along y-axis? So it will be here. There's a one only. Its projection. Let me take a particle. I'm putting a black dot. There's a red dot. Try to follow this. Okay, there's a black dot. So what is this? There's a projection. Let me call particle 2. It will also, what happen as this particle moves, when particle 1 is here, its projection will be at origin. Since this is moving, so this should also have velocity. Okay, agree this. Then after some time, so when particle 1 is here, its projection what should be, on y-axis. No, this was moving with a constant speed. Write it v, where v equal to r omega. What about its projection? Its projection will have different speed. So therefore, let me write v, that is. So this is the initial velocity v naught. That will be at t equals 0. The projection of that particle will be at origin. After some time, it will be at this particular point. Now you can ask questions of why you are taking that projection. So let me take this displacement y. Okay, look at clearly now. Till here, no problem. All of you, coordinate geometry, idea of projection. Fine. This is so. Why do we are discussing all these things? Okay, now by the time we got telescopes and the scientists started exploring outer space, what they saw, there's suppose say this is the some planet or something, let it be this one or anything. They saw some heavenly object. It was revolving. So we know gravitation also. So based on that, what we can say that it will be revolving in a circular path about this. Let's assume that one. So what the scientists, what happened when they made observation, what they noticed is like this particular heavenly object, which is there, no, it was describing to and fro motion. It was describing a to and fro motion. They got shocked. How come an heavenly object can describe to and fro motion? Because if the object is far away, how do it appear? Though it is moving in circular path, but for us, it is moving in circular path. But if you are far away, what happens? How do it appear? It will appear as if it is moving in to and fro motion. Am I right? I think this you can experiment. You can experiment. You ask your any younger brother, elder brother, sisters, ask them to move any object. You ask them to pen, eraser, or something which is clearly visible for you. Ask him to move it in horizontal circular path like this. No, not vertical, horizontal circular path. That one. You view it from near. You say it's in circular path. As you move away from farther, means you are at a distance of say like some 50 meter, or you can say like a 20 meter or 30 meter, no, or say even 10 meter. You feel as if this is moving in a to and fro motion. This called like a to and fro motion. All of you, I think you are having some basic idea of to and fro motion. I need not to stress, sir, what do you mean by to and fro motion? So this will be to and fro motion if it is like this, no? This called like a to and fro motion. This particular heavenly object which is moving in circular path about any other planet or something, no, it will be describing a to and fro motion. It appears, but actually what happened? It is describing circular motion. From there, what happened? They brought this particular concept. Okay, this is very much, I think, let me try if you are able to. I need late. Okay, this is the reference, so you can see, like, you know, you move away from the screen and try to observe. So you feel as if it is moving like this. The simplest explanation is what I wanted to give. I don't want to talk more mathematically. If it revolves around my fist, this particular lid of a bottle, that one, if you view it from far away, if you view it from far away, if you view it from far away, it will appear as if it is moving to and fro motion. It's describing a to and fro motion. If you are moving far away, what will happen? It will appear as if it is moving. It is describing. So what is the reason for that like that? If you are from far away, instead of circular path, what you see the projection of a motion described by a particle. That'll be visible. Don't think that it's imaginary. This is what we feel. I suggest you, everyone, you can do this experiment. You just ask your younger brother or sister to move an object in a circular path around some fixed point, center point. Try to view it from near and further. Not even 100 meter, 10 meter, I think sufficient. Even 5 meter in classroom, I used to show it in physical classroom. No, like the last benches, they used to say, "No, sir, you are describing to and fro motion." The front benches, they used to say that, "No, sir, it's in circular path." What is the reason for that? It's a human high perception, that one. If you are from further, what happens? It will appear as if to and fro motion. Okay, now if a particle moves in a circular path, its projection along y-axis will describe along x or y-axis. I am considering y-axis. Its projection along y-axis will describe to and fro motion. I am interested to study the motion of this projection of a particle along y-axis. That is what very important. For that, what I'm trying to design a mathematical formulas. Means till now, see, like we have studied all the types of like a motions here now. Now there's the first time what happened, we are going to study the to and fro motion. So this will be, so let me do one thing. There's a some asteroid, I'll write it. There's a planet here. So there's a circular path. There's a path of asteroid seen from observer from far away. Seen by observer located far away. What is this circular path? In fact, it is describing circular path. Let's not say like a why it will describe circular path. We know enough gravitation. The gravitational attractive force will power required centripetal force. So we know all that story. Let's not bother here. No, I'm interested in this such to and fro motion. Path of asteroid seen by observer located far away. What is this motion here? No, this is a circular path motion. To and fro. To and fro motion. Okay, this to and fro motion is what I wanted to show. I think I'm very sure that we have not discussed of that kind. Am I right? Till now we didn't discuss to and fro motion. We know kinematics, projectile motion, circular motion, non-uniform circular motion, all different things we brought. Elliptical orbit, circular orbit, all everything. The to and fro motion is what we are going to discuss now. Based on that is what the whole our chapter is. Got the idea? That's the simplest thing. Students see, like this is what happens here. Like if you refer some read good books, no, the good books open rather than focusing more on no, they give examples like this, then they come back here. Most of the books directly they'll start. Okay, particle moves, its projection will move. Students will answer, why projection will move? Who will see this? If you are far away here, you see the motion of this particle as something like this. Getting this one? If you are very, if you stand at center or near, no, you definitely you can say that it's moving in circular path. Simplest reason. Okay, let's do one thing. Let me take help of this triangle. I do notice some triangle. So sine theta is equal to y by this r, let me call a. Hmm. So that's y by a. So y is equal to a sine theta. From here, theta, what we can write? Omega t. And tell me what is y? Displacement of particle, which is describing to and fro motion, or displacement of projection of a particle revolving in circular path. So y is called as displacement. Then by the time when particle reaches here, it will have the projection, this particle 2. So there is no, again see, I have to say particle 2, but actually this is a particle. And what is 2? 2 is a projection. So I'll put it, somebody is asking, sir, why 2 particles you have picked up? I think definitely, okay, no, what is the dot means what you should write? What is the red color? Particle. Particle moving in circular path. What about here? Projection of particle. Path described. Okay, I agree this. So, this 2 is not a particular. 2 is not a particle. 2 is what? Just like it's a projection of the particle. Particle is moving in circular path. That's all. Okay, I brought it. So what is this? There's a displacement. And what is A? A is called as maximum displacement. We'll call that as, very good name will give. We'll call that as amplitude. Like this, what happened? The terms will give names. So this is called as amplitude. What is T? What is next to omega? Angular frequency. I think we know these things from circular motion. What is T? Instantaneous time. What do you mean by amplitude? Maximum displacement from mean position. I'm going to take this as mean position. This I'll call it as upper extreme. The terminology is very important. Almost all numericals, the same set of formulas will be using. This is called as upper extreme, and this is okay, fine. So this is like, so I won't know what is the speed of the projection, what is the speed of particle, or what is the speed of projection, that one. So I'll differentiate. Let me go for dy by dt is equal to a omega cos omega t. So dy by dt is what? Velocity. Once again, let me differentiate. Dv by dt, a omega square sin omega t. Dv by dt, what you can write? Acceleration. And what do you mean by this a sin omega t? We'll get like this, a equal to minus omega square y. Or I'll rewrite. So this will become, okay, now look at this. What is acceleration? Acceleration proportional to negative of displacement. So what happens in SHM? In SHM, what will happen? The displacement will vary as a harmonically. Sine and cosines are harmonic functions. And look at the speed of particle, it also varies harmonically. Look at acceleration, it also varies harmonically. It also varies harmonically, you see that one, acceleration. Okay, let's talk about the, what is cos omega t. I'll try to replace. Cos omega t, I can write as root of 1 minus sine square omega t. What is sine square omega t? Y square by a square, or v is equal to omega root of a square minus y square. So what is the speed of particle? The speed of particle, is it constant? No, it will be varying, is telling. So this will be moving with a constant speed. So what particle one says, I am moving with a constant speed. What about the two will say? Projection, it's projection. No, 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 I'm accelerating. It's this projection. So shall, in simplest way, for a common man or woman, both, or common person, let me call. For a common person, what mean? Shall I say shadow? If you run like this, what about if some source is kept here? It will form, due to that source, a shadow will be formed. No, if a person runs with a constant speed in a circular path, is the shadow what will happen will describe this motion, which is gone by these equations. So this person will be running with a constant speed. What about his shadow? Shadow will describe non-uniform accelerated motion. You see, acceleration itself is varying here. And how do I express that? Will with help of this one. Okay, look at this one. Now the person runs with a constant speed. So here the speed will be maximum, speed of the shadow. So the person will be constantly running. But what about the speed of shadow? It decreases. By the time person comes here, what will be the speed of shadow here? Will be zero. Sir, how do you can say? You have this equation, put y equal to a. If you put y equal to a, because what are the things now? This point is y. This is x-axis. Okay, if you look at this, so if this is the origin, then y equal to zero, maximum speed, the speed of particle decreases. So what type of motion the shadow will describe? Non-uniform accelerated motion, not only uniform accelerated. Can you apply equations of motion to work out anything? No, we don't know equations of motion. When it comes SHM, we don't know equations of motion. Are you getting? No? So the shadow is describing, I say that the shadow is what describing a simple harmonic motion or what you can call to and from motion. Now, why the name of chapters are simple harmonic? Look at this displacement of the shadow or displacement of particle describing to and from motion. Let me directly say it's a particle now. It varies sinusoidally. Speed also varies sinusoidally. Look at acceleration, it also varies. Next, I'll bring kinetic energy, it also varies harmonically. So all the quantities are varying harmonically. So what is the type of motion? It's a motion in which the quantities are varying harmonically. Displacement, speed, acceleration, kinetic energy, even potential angles, I'll bring it. So harmonic motion. Why simple? I think you know trigonometry. If I give any problem related to sine theta, cos theta, all are very, you all are very good, no? That's why the name simple. Sir, what do you mean by complex S? Later part I'll introduce. What do you mean by complex? That one. So the mathematics, what we are going to notice, it is a very simple trigonometry, that one. That's why simple harmonic motion. Got the idea, no? Shall I say that your chapter is over if you know this much? Rest all everything is what happened, the extension of this, the application of this one. Okay, fine. So there is no such particle 2. What is that one? Only particle 1 is what moving, and the 2 is what? Projection of particle. Where is the particle? Particle is moving in circular path here. 2 is what? 2 is not a particle, it's only a projection. That what happened? Initially I derived it. Okay, look at this. So there's the expression for the speed of particle, and look at how acceleration will be proportional to negative of displacement. Okay, let me directly come only for Okay, let's again continue with the same thing. Particle is here. These are the instants of time. At t equals 0, particle 1 is here. V. Okay, they like this. Huh? Now, what about its projection? Its projection here will be at this particular point. Then afterwards, okay, let me give number 1 when it is here. When particle 1 is here, when particle is a position to its projection will be moving with a velocity v2, v1, v4, v5, v6, and these are the very basic fundamental things. Okay, look at now. So these are the things. So now look at in all the positions, what happened? The particle is moving with a constant speed, but its projection weapon is going to describe a variable accelerated motion. So this is I'll call mean position, upper extreme, lower extreme. Okay, let's analyze one thing now. So as this projection moves, so initially this should have a maximum speed, no? And here, what is the state of this? Instantaneous rest. So here maximum speed. So here we'll introduce Vm. It's a position one of the particle only, but here speed will be maximum. And what about here? Instantaneous rest. What? Not particle, it's projection. So what type of motion when it moves from mean to upper extreme? Retarding motion. So how the acceleration should be directed? Towards center. So whether particle moving from mean to extreme, okay, this is the mean. Upper extreme, shall I use word only symbols? Lower extreme. Mean or equilibrium, anything you can call it as. Okay, no. So now it's having maximum speed. So now you can say maximum. Already we have equation. Put y equal to 0. There'll be maximum, no? So how much that is equal to, this is equal to A. Okay, I'll begin like this. So it'll have maximum speed. So it'll undergo retardation. Okay, how to calculate V2? If I know this displacement y, I'll use that formula V2 equal to root omega root of, what is the speed of particle? Omega root of A square minus Y square. I take help of this formula. Then I'll find out the speed. When the particle is at upper extreme, put y equal to a, it will be instantaneous rest. Again, what will happen? The speed of particle will increase. Then it will be maximum. Look at now how the acceleration will be always directed towards mean position. Shall I put it here? The particle describes the simple harmonic motion or the basic necessary condition. The acceleration will be always proportional to negative of displacement. Fine. So shall we put here like a here how you have to show acceleration like this only A2. Now how it will be A3? It will be like this. What about A5? A5 should be like this. What about A6? It should be like this. So it anywhere, how the acceleration be always directed towards mean position. There's a one basic necessary condition. Acceleration directed towards will be always that this word is a lot of this weightage always be directed towards mean position at any instant of time you can pick up. Okay, there's a one meaning of a equal to minus omega square y. Okay, I think now we are in far better position. Next question comes like, sir, is there any object which describes such to and from motion? Can you give example? Okay, fine. This is about the mathematics. Is there really any such object which will describe? My answer is that we know already. We have done so many numericals also. Sir, from where? Go back to work point G chapter. So what is the motion described by the spring block? It's a to and from motion only, and that's called like a oscillatory. Okay, let me introduce to the spring block system. Is this okay now? So like even acceleration also is varying with the time. So what is the equations here? Y equal to a sine omega t. Speed is equal to a omega cos omega t. Acceleration is equal to a omega square. So once again, I'm writing. These are all basic equations what we have come across. So look at all these quantities. They vary harmonically with the time. Let's plot graphs also. Once again, let me take it. Let me plot graphs of all this one. This may not be needed. This, I think you are very good in plotting graphs of trigonometric